Um, Thanks for coming out this morning. I know it's early, but we have no control over the conference start and end times. Normally I'd start at noon and end at 8, but that's the way it is here. Thanks for coming out again. My name is Dan Pollock. I'm the CTO at a company technology consultancy called Data Storage Science. My co-presenter is Jessica Bresnahan. She's over here. She'll talk about some of the details of our project. And we'll take you through kind of what we did, why we think it's interesting, what it actually does, and how it actually does all of those things, and then what's next on the list of to-dos, because this is a work in progress, and we felt that earlier to kind of get people aware of it is better, and it turns out that people are talking about this sort of thing more and more and more as we look at how data is managed and also how to integrate artificial intelligence capabilities into storage systems as a whole. So that's the nature of this. And so we've built the plug-in AI engine for an object store, and the reasons for that will become apparent as we go through what it all is. And that's sort of the high-level outline. I'll take you through the actual details. One quick note is that I've committed a conference foul. I've actually reordered and changed some of the slides. So what's in the conference website won't match exactly, and I'll see if I can upload those for just the sake of completeness if people want them to download later on. So what are we building? Like I said, it's a plug-in AI inference engine for object stores. And I realized when I created the slides and was looking them over that I should probably talk about inference for a second, because not everybody knows everything that we know. So the definition of inference is this conclusion based on the evidence and reasoning. AI modifies that in certain ways, in that you don't really take into account evidence. You replace that with domain-specific models that are trained on specific information. So that replaces the evidence part of the inference process. And then reasoning, machines don't reason, that's for sure. So that's replaced with statistical probabilities of what's in the information being inspected in inference. So that's what the AI engine does, and then what it does too is what we're going to talk about here and how it does it. The object storage systems are a good place to start because they store a lot of unstructured data, and a lot of people put a lot of things in them that may or may not have real awareness, or the people who manage those systems may not have real awareness of what got into them. They become large dumping grounds. People put tons of data in them because they're cheap and they're easy. And in the end, if you're lucky, you tend to know who put it in and when they put it in and what kind of file it is. But beyond that, people are really lazy about putting real information about their data, right? The metadata that goes along with it. So you know what's in the files that you're storing. And that's important when there's interesting or sensitive or unusual data in the object store and you don't know about it. The nature of it, like I said, is that the groups who manage it are different than the groups who use it. And because of that, the groups who use it are sort of, ever consuming and really without rigor in the way that they store and take care of that data. And so that falls to the people who run the systems, and the people who run the systems have no idea, like I said, what got in or when. So providing more insight and shedding more light on what goes into these systems is always helpful. It's still work in progress, so we have certain capabilities, certain other capabilities don't function as well as we would like or at all yet. And I'll talk about what the roadmap looks like as well. But that's effectively what we are building. So now we get into why this is interesting, and I touched on some of this, which is content awareness gets you better utilization and better data management, right? Like if you know what it is, you can treat it in different ways. And that's important for the systems managers that run the backend object stores, but also for the organizations that own them in a lot of different ways. Our system can do the discovery of multiple object types and figure out what's inside of them and then create records about what's inside of them in the object store so that they become searchable and identifiable. And in the event that you want to do something with those identifiable attributes beyond who created it and when, but what's in it, you can apply real policy to it, and that's important for things like data leakage. There are a couple of interesting anecdotes that go along with this that I've discovered over my research. The most recent one, I'll go first and then I'll go back in time, but this week, Microsoft submitted for discovery a bunch of documentation that included non-disclosable, not public information about Xbox. They were really embarrassed by that. So what happened was they shipped a bunch of files off to the FTC for this court case, and the FTC made them public because that's how discovery works. And it turns out there's a whole bunch of stuff in there that shouldn't be in there. And systems that, like the one we're building, don't provide absolute security against that kind of disclosure, but they absolutely do provide another set of guardrails. If they had said, let's take the giant set of documents and run them through the discovery process, we'll put them in this object store, the object store will crack them open, figure out what's inside of them, flag all the things that we think are important, and tell us stuff like, there's a prototype Xbox picture in there. And then we won't send it to the DOJ without taking that stuff out or redacting it in the way that is appropriate for whatever legal process there is. But that's kind of the idea, right? And so because somebody probably dragged and dropped a giant folder and then shipped it, nobody noticed what was in it until it was too late. There's another behavior that I came across, and this is, it's reported, so I'm taking it on faith that this is correct, but apparently one of the things that social media companies do is they rely on viral video to drive their numbers up, which generates revenue in some social media sphere way. And in order to do that, getting a hold of viral video is what one of the goals for those sorts of companies. And one of the things they do is they try and link to videos that are popular from rights holders that aren't them. And the way they do that is they create links to the videos that they don't have rights to through accounts that are throwaway, basically, and then they link to those. So embedded sort of sharing of other people's links to real rights holders' media allows them to bypass copyright and not pay those rights holders. And whatever you think about that, that actually happens. And the reason it happens is because, according to the article, the folks at Twitter and other places that share viral video don't actually know what's in the video unless you tag it with text. So if you tag the video with text, I can discover who's in it and who the rights holder is and all kinds of things like, you know, this is a baseball game that belongs to Major League Baseball and, you know, it's the New York Yankees or something like that. But if you don't tag any of those things with text, all you do is show the viral video of the home run or whatever, the umpire yelling at the manager or whatever you wanted to show. It's very hard for the platform to discover that that video belongs to a rights holder that's not the person who shared it and take it down. Our system can do that. It'll tell you who's in it, who, where it is, what it is. It'll give you the audio transcript of it if there is, those kinds of things. So the idea there is that you can save yourself from that sort of exposure and avoid a long chain of somebody has to violate your intellectual property rights as a copyright holder and then get it taken down versus just never having it go out in the first place, because the platforms will take care of that if they know that the video already belongs to somebody who isn't the sharing owner, right? So those are kind of reasons for why it's interesting. Additionally, the Cloud Storage Technologies Initiative here at SNIA thinks it's interesting. In June, there was a presentation on data fabric. And one of the things that they want to do with the data fabric initiative or in the cloud storage initiative is to create awareness of what's in the data. And this is a slide straight out of the presentation about halfway through that basically says we should do content inspection of the unstructured data with a part component of the data fabric. This doesn't exist yet in this presentation, but ours does this. So I thought, gee, that's neat. The cloud storage technologies folks from SNIA are actually saying we would like to have this. And they're talking about slightly different storage systems, and that this was file shares, not exactly object stores, but I think if you squint at those things, they're kind of the same thing these days. And also having this working seems like we could move their agenda along in addition to helping folks discover all the things that are in the storage systems as a whole. So at a very basic high level, because it's an object store, we can watch for events in that object store, and we would just watch for object creation events. And once we see the object event come in, the server that's looking for those things says, what kind of object is it? And by type, we decide how to go about looking at the different aspects of the file. So Jessica will get into the details of some of that a little bit more, and then I'll kind of go through examples of it after that. But the idea is that once we know what the type is, we can select the appropriate inference operations for that specific type of file, depending on what it is. And then whatever we extract from that file, as far as different types of data and information, we can then run further inferencing against them if there are second order kind of data types within it. And video is a great example of this because it's both pictures and audio, and you can do a lot of different things with pictures and audio, and in some cases text, right? So it has all of the different types that we can evaluate. And then the last thing we do with it is we'll go ahead and we'll index all the content. And once we have the content indexed, it's searchable. And once it's searchable, it's discoverable. And you have to ask the right questions. We still haven't figured out how to help you with that, but we can definitely flag things that you already know you want to know about. So if you were the Xbox people, you would say, always find the word prototype. And if you find the word prototype, find that document and make sure it's redacted properly. So Jessica's going to take you through how it works.
Good morning. I'm Jessica Bresnahan, and I am the college student that built the Flask framework for the AI inferencing tool. So pretty much this is just a visualization of how it works. An object event is created, and through webhook, the Flask server accepts that, and then it reads the request and it sees, oh, this is like, a video file or a text file, and then it, based on whatever the file type is, it will start running through processes to inference, whether that's, like local or cloud inferencing. For example, we use Azure for OCR, and we also use OpenAI for audio transcription. And, when it goes through all the processes, once it's done, it puts everything back in the object store and, just keeps going, rinse and repeat until everything is inferenced, puts the output files back into the object store, and yeah, that's how it works. And this is just more of a broken down of how it does it, like the webhooks, object creation, run the inference, and then put it back into the object store in its directory with all the results. So, yeah.
So Jessica's new at this, so I'm going to do a little bit more detail, but she's awesome. So the idea here is that, like she said, use the webhook, which is notification from the object storage POC that we're doing, but doesn't have to be webhooks. Can be anything that's supported by the object storage system that you're using. By default, these days, almost everything supports webhooks, multiple queue systems, right? So if you're in AWS, you have SQS, but you also get choices like MQTT and a bunch of other things. And then a lot of the systems also support sending events to databases, and traditionally the reason for that was just kind of logging of what was happening within the object store, but because you already have a notification that an object has been created, you now have an event and you can do something with that event. So that's where the event-driven part comes from. And it's fairly straightforward to integrate. Like Jessica said, the implementation we're using is Flask because Python is quick and easy, and all of the libraries that exist for the inferencing generally have Python toolkits or SDKs. And then, like I said, the rest of the process is interesting. The last operation where we flag it as complete is sort of interesting because that gives us a little bit of robustness that we can do things like discover that inference processes have not completed properly and rerun them. And we can also look at what's been completed when and kind of go back and do a lot of sort of systems level stuff that's more my thing than her thing. But if you want to turn this thing into something that not just I can use, but other people can use, you have to add a bunch of robustness and capabilities just around verification and usability and recovery and those kinds of things. So that's why I had her put that into the system. This is even more detail about how it works, but the nice thing is that now kind of enumerate the objects that we detect, right? So images, text, audio, and video for sure. At this point, we can probably do other types, but we haven't found those super interesting because if it's not super interesting, then it won't motivate us to do the work. So like, and there are other people that do those things better. Like you can do CSV files and you can do all kinds of other specific types of files. But we started with, and CSV I guess is text, but I'm thinking more along the lines of verbiage text, not spreadsheets. Anyway, so we run those inference operations and we do all of them based on the types of files that they are. And there are right now, I think just about 25 or 27 different operations that we can run at any given time based on the file types and what comes out of those file types as we open them up and discover the different types of data inside of them. And the other interesting thing here is that in most of the demonstrations that you get from the AI communities for video or images, you get to see like bounding boxes and things that are identified in the in situ video so that you can see overlays basically of what we've discovered about either the image or the video or even the text. That's great for showing people, but it's not great for searching. So we take all of that information and we just output it as text. And we've started wrapping that text in more structured formats like JSON, so it becomes more searchable for standard tools that can do search off the shelf, things like Elasticsearch and OpenSearch, right? And then, like I said, we flag the operation, and that's important for systems things. So here's an example of just kind of the workflow, right? So it's that same kind of diagram of what happens, but it's specific to the character recognition behaviors for a PDF file. And so when you take a PDF file, you assume kind of that it's text because that's a document format for the most part, right? But documents these days are pretty rich. They have images in them, they have text, they have other things sometimes, right? So we run it through the process, we get out whatever the text is because we assume it's a PDF file, but we also do things like look for images and pull those out, and then we look in the images and decide what's in them as far as what are they, you know, or what do we recognize in those images, and then what do we do about the things that we recognized in those images. We do object detection, we do people detection, and these are all off-the-shelf models, so we're not doing anything exotic here. We're just basically end users of the AI tool sets that people provide in various ways, either as open source or, like we said, as cloud services and things like that. So here's an example of how that works for real. So I took this is like a 2020 Artemis project PDF about going back to the moon and how, lunar landing EVAs will work. And the first page of this is an introduction by Jim Bridenstine, who is the time NASA administrator. And so what do we see here? Well, we see that there's a person, and we have all the key points on that person's face, so we know kind of the locations of those key points, and we've detected a human being. And then we take that face and we run it through sentiment recognition, which is another thing that sort of works depending on how much credibility you give to that. And you'll see on the next example, it's sort of hit or miss. But here, it's pretty good, and it's discovered that it's given us the bounding box, and it's discovered that he's smiling, so it's assuming he's happy as an emotional recognized facial expression, so that if you're looking in the store for at some point happy people, you're definitely going to find Jim Bridenstine's headshot here from this document. And then the other thing that we do is we pull out the entire text of the document, and so that makes that text now searchable in a way that the PDFs are. And PDFs are a pretty straightforward document type to work with, so it's not terrible, but there are other document types that are way worse to work with. TIFF, for example, is one that has been used for a long time for things like faxes and e-faxes, and people probably have an avalanche of this data. One of our customers that we work with, you can look them up because we're public and we are public about who we do work with, but I'm not going to mention it here. But they definitely have a ton of TIFF data. And that TIFF data is incredibly difficult to use and search and discover what's in it without what they do today, which is sort of very involved processing, and in the future, hopefully, either we will help them with or somebody else will help them with turning that TIFF data into more useful, searchable data for consumption both by the public and internally. And so this is an example of how OCR goes. But then we can do regular images as well. And you say, well, didn't we just do images? Well, we did images secondarily, but images are also a source sometimes, and images also have things in them that aren't always just pictures. Sometimes there's text, and sometimes there's people in pictures. And so when we pass the images through the process, we get all of those things out as well. So we'll do text, and we'll do text segmentation, and I'll show you what that looks like, and we'll do, once again, facial recognition if there are people in it, and sentiment recognition for those people. And so this is a Coca-Cola ad. It's got Taylor Swift in it, and people recognize her. So this is a good example because you can do a bunch of interesting things with it. Still recognizes the faces, right? Get all the key points, say this is a person with a face. Great. Then it looks at the sentiment. Theoretically, our sentiment says that she's got a neutral expression. I suspect the Coca-Cola people would hope that she would have a satisfied or happy expression, but like I said, the subtleties are kind of lost. And if you look carefully, I think you'll see that she's not exactly got a neutral expression. And then one of the other things we do is we segment the text that is in this ad, and we pull all the text out, and we pull the text out with its locations. And that's what the text box at the bottom is. It's kind of an eye chart, but the idea is in the PDF file, we could just pull the text out and show what the text said. In the ad, the text position may or may not be important, so we're recovering that as well because it's not a document for text, it's a image that has text in it. And one of the other interesting things about this is that the segmentation parts are able to do things like pull things like license plate numbers out of images or road signs out of images. So that's how the license plate readers work, right? They do image segmentation, so they take a picture of your car, they find where the license plate is, then they read the characters off of it. That's exactly what this is doing, and we're using the same tools for that. There's nothing remotely exotic going on here. The other thing you can do is like your car, when it looks at the road signs and tells you what the road signs say. My wife has a car that reads stop signs and speed limit signs and then puts them up on a heads-up display. That's using this technology, right? So it looks at has a camera, sees what's going on, finds the specific road signs through image segmentation, then pulls the text out and then displays them to you. In this case, we're not displaying them to you, but we are pulling them out and making them searchable for indexing. So there are a bunch of exhaustive examples here. Doing a demo probably would have been a little bit tricky just because of the internet and all the things we would require to connect to the system back in the world. So I'm just going to take you through a couple more examples and then go through kind of what's on the roadmap. But once again, audio is kind of an interesting one. People do audio transcription of podcasts today. This is how this works. There are a bunch of other good ways to do this, but one of the other interesting things about the inference types that we've got in there is that if you've got foreign language audio, we can translate it. And we can give you a transcription of it both in its native language and in its translated language. And those are capabilities that OpenAI provides through their Whisper tool. And we can connect to that. So it gives us the ability to do inferencing locally, which most of our image recognition and text recognition is all done locally. Some of the more advanced and sophisticated stuff where there aren't locally available models yet or locally available inferencing capabilities, we ship those off to whichever cloud provider is giving, is providing that service. So like Jessica said, some stuff goes to OpenAI and some stuff goes to Azure, but we have the ability to connect externally, and you can manage the system however you like to allow that or disallow that based on what your requirements are within it in a real world implementation. And then video is the richest format of all of these, and it gives you numerous opportunities to do all kinds of things. You can extract the audio and do audio transcription. You can make that searchable. You can find the people in the videos. You can find objects in the videos. You can look at the paths of people and objects in the videos frame by frame. You can do things like image segmentation on the individual frames, which allow you to do things like extract the slides from a video presentation. So at some point in the future, I'm going to pull this video up when the SNIA folks publish it, and then I'm going to have the system store it and see if we can pull my slides out of this video presentation depending on how it's been formatted and whether or not we can do segmentation on the individual frames to pull those slides out and see if I can regenerate my presentation from the video. And that's going to be one of those proof of concept things that I think is kind of interesting. And then, like I said, once we have objects, we can do paths, and people, we can do paths. And the other sort of interesting thing about this is that just like in the image example where Taylor Swift is in that Coca-Cola ad, if you train a model specifically to do not just people recognition, but individual recognition, right? So you can recognize that in videos or in images or what have you, you can see people that you know or that you know of, like Taylor Swift. And one of the things that we've done on a different project in the office is to start recognizing folks who work at DSS. And so there's a computer in the office that recognizes me. And there's a computer, and it recognizes like Nicolas Cage, among other things, because Jessica thought that was amusing. But the idea is that if you have a sufficient training set and the image training set for individual recognition and identification is actually very small, just a handful of images, you can pretty reliably recognize those people in the images. And that gets you back to when I search for things in my object store and I don't know what all got in there, I can find things like show me all the pictures of celebrity X. And when I do that, if I'm a media company, I can use them, look through the photos and say, that guy was, in the news, let's pull out a photo and write an article. And now I don't have to go send a photographer out into the world or, rely on, hopefully somebody tagged all the images properly of the celebrity we're looking for. And the other interesting thing about that is it works the other way too, in that you can say, we should never put these types of data into our systems, and you can flag them immediately at the beginning for any sort of specific types of data that are either sensitive or disallowed for whatever reasons. Things like social security numbers are a good example of that, right? This is maybe a content serving object store, it's an origin for web services. Somehow somebody took a picture, that picture includes somebody's social security card for some unknown reason, but it does. Now you would find that and never put it out into the world beforehand. And that makes these systems sort of powerful and interesting. So get back to this diagram. Just a couple notes on this. The idea that we can send the inferencing operations wherever is really useful. And there's nothing magical about that, but not having to be constrained by just one set of inferencing capabilities makes it extensible. And so a lot of people are adding these tools to their systems, but they're not necessarily making them extensible enough to add these tools to their systems and say, oh, there's a new image recognition model that I want to add, or there's a new audio tool that I want to add. And so the extensibility here is that we just basically look around for whichever models are interesting to us and we think fit with the data types that we want to analyze, and we add them. And for instance, a couple months ago, the Open Computer Vision guys created this thing called a model zoo. And the model zoo has a number of interesting capabilities. And I walked over to Jessica's desk, because that's kind of what I do. And I said, hey, the model zoo has all these things in it. How long is it going to take you to add them? And so we went from about a dozen inferencing capabilities to about 24 inferencing capabilities, because she just decided to go crazy and add them all. And that's great, because none of this was really a lot of effort to add them all. And I say that because I didn't do the work she did. And so the other interesting thing about this diagram is that even when you're doing locally, there's an opportunity there to do locally on different types of compute complexes. So today we have a fairly simple Python Flask server, and it runs on a general purpose CPU and just kind of watches for webhooks and gets connections and does the work. In the past, I have done this work with computational storage devices, sort of nascent ones, and the idea is that because there was a general purpose ARM core sitting on my storage devices anyway, I was able to ship requests off to those ARM cores to do the inferencing locally, and that avoids some of the data transit, and that improves efficiency and lowers cost, and theoretically, and then also lowers network dependencies and all kinds of things there, right? So you can do computational storage stuff, which I think is really nifty, and isn't just the usual, like, we can compute RAID erasure codes and compression and encryption kind of stuff, right? This is actual things that make me interested in it, as opposed to like a lot of math that makes my head hurt. And the other thing is, if we have really more advanced requirements, we can then use GPU inferencing as well. We don't do that at the moment, but there's no reason you can't. And then you can use other coprocessors as well, right? TPUs are available, DPUs are available. Any of those things can be added into the inferencing capability set just by writing the appropriate code, because the back end effectively just ships the work off to wherever it needs to go. And so here's the roadmap-ish. I mean, this is my to-do list. And like I said, so one of the things that we need to do is add a little system reliability and robustness around this system as a whole. And so eventually we'll have a background process that'll say, I have this file, or I got this event, and I'll look at the event queue sort of historically and say, is there a completion file that goes with this? That means I ran through the entire series of expected inferencing operations and I got done. And if there's not, we'll try it again. And then that'll also enable us to do things like rerun inferencing if a new model, like I said, shows up in the model zoo, and we want to say like, oh, let's run all the images of type X, Y, or Z through that model again, right? So maybe we have an elephant detector now because we're trying to keep poachers out of national parks. And the idea is that before we couldn't detect elephants reliably, but now we've added reliable elephant detection through some new model. Find me all the ones where we detected elephants originally and rerun them. And then say, are they really there? Or, have we done a bad job originally, or have we done a bad job this time? And you don't get full coverage, right? Because there's always like the stuff you don't know, and stuff that doesn't work. but you still get the opportunity to rerun those. And so we'll build some tools around rerunning inferences against different types. Or sometimes you detect the wrong type of file and you say, oh, we had a bug and we detected all the TIFFs as JPEGs and they're not right and we should run them through TIFF OCR, not JPEG facial recognition. And then one of the other things that needs to happen is that we need to figure out how to work with people's encrypted content, right? And the idea here is that as data security becomes more and more important, more data is going to become sort of opaque to the system that manages it, which is great because it offloads that responsibility elsewhere. But for the systems that manage it, opaque data becomes much more difficult. Again, that's why we're opening these up and looking what's inside of them to begin with. So the idea here would be to establish a trust relationship with the people storing and retrieving the data and find a way that makes everybody satisfied from a security perspective to get keys, decrypt the data securely, look at what's inside of it, throw away the data, right? Because theoretically you're just working on a copy, or maybe you're working on the real one, and then re-encrypt it and then encrypt the data, the things that you found out about the inside of it, and put those back in the data owner's data set, and update your searchable records with the aspects that you discovered, but also make that system encrypted and secure so that only the customer who owns the data and the database that is searchable belong to them and use their keys, but you've done all the work on your back end. And that's more of an order of operations and a trust establishment process than it is a really technically complicated one, but it's a thing we got to do. And then one of the other things is today it's a very simple system, so it doesn't really have to scale up and down. We don't have 100 million objects in there. We have probably 100 objects in there, and that's just because we kind of do the evaluation. And obviously we know this doesn't scale, but that's fine. The nice thing about this is it's an embarrassingly parallel problem. Every file inference is a separate operation, and every operation against every file is separate as well, so we can run them all in parallel. So if I want to run 100 inferences at once, I can run 100 engines and ship the data properly, and that becomes a workload management problem as opposed to a real scale problem. So as long as I have enough compute, I can scale up as long as I want. And the other thing that we want to do is add load balancing for incoming. So if I have more than one compute inferencing engine, I will obviously ship the work off in a load balanced fashion to the available resources, so I don't have things like availability problems, and I don't have bottlenecks, and I don't have long queues for the output operations. A lot of these operations don't run quickly. They're very involved, and they take a non-trivial amount of wall clock time, so scaling up the number of backends for a higher throughput system is definitely on the to-do list. And like I said, on the sort of diagram slide, we're going to run on alternate compute. We already do, or we already have in the past in some cases, but we'll move this more to whatever sort of devices come down the road. And if anybody wants to loan those to us, we're happy to take them and do the work and then talk about it. So for all the CSD physical device guys here at the conference or who watch the video, get a hold of us and we'll run our tools and our engine on your hardware. So that's all I got. I hope it was informative or interesting, or at least kept you awake most of the morning. Are there questions? Yeah.
Volker, do you have an idea of the cost of doing this processing per terabyte?
So so the question is, do we have an idea of the cost per terabyte of these operations? And the answer is we haven't really looked at that yet. There are definitely costs associated with the system, but they're fairly straightforward to know. So I think, now that you've mentioned that, I'll go home and take that as a project and go discover what it is that each inferencing operation costs. We know from the cloud side what those operations cost as far as the inference as a service providers go, right? So we get a bill from Azure and we get a bill from OpenAI, and it's, whatever 2 cents per whisper translation that's up to 20 minutes long or something like that, or it's something around those numbers. But it's a well-documented price book, and so we can kind of to go discover that. But yeah, it's a good idea. I should probably go figure out what is the back-end inferencing process cost per terabyte of inference data, and probably also a couple other aspects, but it's a good question, thanks. Anybody else? Yeah.
So you mentioned that example with Xbox.
Mm-hmm.
But let's say they prepared, like, I don't know, 200 documents
Mm-hmm.
with hundreds of pages each. And the inference process would condense that information, of course, but still, like, a lot of data in the output. And how would that help actually realize that there are, like, internal Xbox documents in there? Because someone would have to know what to look for.
Right, so the question is, if you, in the Xbox case where Microsoft shipped off this tranche of documents and they overshared, how would you actually know what was in those documents when searching for them? Because it's still a ton of data coming out the other side. If Microsoft sends 100,000 pages for discovery, how do you know? And the answer is, you got to ask the right questions. We can't help you with that, but we know things like, if you just say, look for the word prototype, that's a good one to look for, right? And finding prototype by paging through hundreds of thousands of documents is hard. And if your documents are not in formats that are readily searchable, so you've complied with discovery, right? Because you want to not have to go to jail, but you don't want to make discovery easy for your opponent, right? Lawyers do stuff like that. I do stuff like that, right? If my opponents are my opponents, I don't want to make their lives easier. So if I give you the documents and they're meeting the discovery requirements, I don't want to make them easily discoverable for you. So I may put them in formats that are difficult to work with. And you might have to print out all these pages. And people have done this, right? They've sent hundreds of thousands of pieces of paper to their opponents to make them go through them in lawsuits. That's just a thing that happens. And so in the case where you're internal and you want people to be able to prevent sensitive data from being exposed, you would make that easier. And the way you do that is you say, we've got these difficult formats, but we can still crack them open before we ship them and run them through the system. And if we have the specific queries, we'll be able to at least detect those things. You won't be able to know for sure because you might not have thought of every possible data type that could leak, but at least you'll have a better chance than I drag and drop the folder and send it without inspection. And that's kind of the idea, is to add better capabilities, not solve all the problems around data exposure. It's just never going to happen, but at least we can help. Question?
What about false positives, especially with analyzing images and audio?
Yeah, so that gets more into the AI models that we use and the training sets that go along with them. And so false positive is definitely a problem. And it's one of the potential use cases for a system like this, right? So if you want to ensure that data you're going to use for training that you bought from somebody who used humans to tag it isn't full of things that are incorrect, you can run it through the inferencing system and potentially discover what it is about those systems and those files in those systems that may or may not be correct. And so false positives are sort of the nature of what happens, but the idea is that if you look at the confidences and tune them appropriately, which is an output from the system as well, right? How confident are you that that's Jim Bridenstine or Taylor Swift versus anybody else? And you can set certain thresholds, and you can be very conservative or very relaxed about that. And once again, that's a human problem. There's not really a good way to solve that because everything is subjective and the machines don't reason, right? So you and I can look at that and say, well, of course that woman looks like Taylor Swift, but it turns out she's an impersonator. And that's a subtle thing that the machines are really bad at. And so effectively, to deal with the false positive problem, you kind of have to deal with, or even the false negative problem, you have to deal with what are your acceptable thresholds for determinism. And unfortunately, that's a lot of words that says, I got to pick where it's good enough and use the metric that they give me to tell me it's good enough. And in the future, work on the models and work on the training sets more to move those numbers to where I need them to be.
You have, sorry, a follow-up question. Do you have something like, you know, captchas are usually used to deal with these things? Is it something that you consider? Or?
So the question is, do we look at CAPTCHAs to deal with people falsifying information, basically, right? And so right now we don't. But like I said, there's a lot of to-dos. So in addition to adding cost awareness to the system, we'll go ahead and add a little bit more provenance to the system as well. And that will help with people's confidence in it. So yeah, that's a good idea. And I'll add it to the to-do list, which is getting kind of long, but sure. Thanks. We got about 2 minutes in case anybody else has questions. If not, nope. Great, thanks for coming.